All right, we're going to get going. So our next presenter is Michel Barbeau from Carleton University in Canada, and we're talking about software-defined quantum stream-ciphers, which is one of the most unique top things at the conference. So please join me in welcoming Michel to the stage.
Good morning, everybody. My name is Michel Barbeau. I'm a professor of computer science at Carleton University. And I also have a radio license, and my course line is D3ENB. I mentioned that because several of the talks were about listening, monitoring the radio spectrum, and actually with the amateur radio license, you can transmit video at not limited to milliwatts. Depends on your license, but you can transmit with hundreds of watts. It's ideal if you are an independent experimenter or if you are in an academic environment and you don't actually experience with software-defined radio transmission. Other than that, my presentation today is about quantum communications. And the reason I have this work, I was trying to find a way to combine 4 things in which I'm interested and that I wanted to teach together: Python, software-defined radio, quantum communications, and cryptography. And I came up with this design that I want to share with you today. So it's a Stream-Cipher that I designed using the software-defined radio approach, and it uses quantum communications. Okay, my presentation is structured in 3 parts. In the first part, I will give you an introduction, a general introduction to the area. And I will give you some background on quantum communications. Probably it's a concept that is new to most of you. Often, if you take a book on quantum communications, they are highly mathematical. Okay? And actually, when you look at the core concepts, they are surprisingly simple. And I will explain them in a simple way, with no mathematics. And I think you will understand. I will give you more background about the application I designed, and we will go through the design briefly of my software-defined radio quantum cipher. Okay, what about quantum communications? Okay. Quantum communications, it's simple. It uses photons to communicate. Okay? Maybe you are already using wireless communications or optical communications. Indeed, you are using photons also. But very likely you are generating, when you're transmitting, you are generating billions of photons. Okay, so you use photons at a macroscopic level. For quantum communications, the goal is to use photons at a microscopic level. Okay? Each individual photon carries information, actually 1 bit. You can encode 1 bit in each photon. Okay, so it's a very small scale encoding. And the word quantum comes from quanta. The photon is the quanta of light, the smallest possible unit of light you can have. Now, in terms of medium, the kind of medium that can be used for that, you can use optical fiber or free space, and light is used in the ultraviolet or infrared range. Application of quantum communications, I believe there are three main areas of applications. One of them is quantum networking. Okay. The other one is distributed quantum computing. And the focus of my presentation is quantum communication, security with quantum communication. Now, maybe you still wonder if quantum communication is for you. Okay? I would say if you are below 30, it's very likely that during your career you will experience the collapse of communication security based on classical techniques. So one of the big threats is quantum computing. And when quantum computing will work, it will break RSA. So quantum communication is an alternative to classical communication security. Okay? And one of the key properties that we are using, so encode. Photons encode, each individual photon encode a bit. But the thing is, the main property that we use, and maybe if there is only one thing you could remember from my presentation today, it's that thing. When you measure a photon, so actually we're reading a value in quantum computing or quantum communication, we use the term measuring to determine the value encoded in photon. We measure it. Okay? And the big thing is when you measure a photon, you can actually destroy the state. Okay? You cannot measure a photon without affecting the state of a photon. Okay? So it's single read. Okay, you write and you can read just once. And that's the property we exploit for secure communications. Okay, now the background, a little bit about the background behind that. Now, when a photon travels in space, it vibrates, okay, according to a certain angle. Here on the left, I picture in an abstract manner two photons. One blue that vibrates horizontally, and one red that vibrates vertically. Okay? So this is called the polarization of the photon. And we encode the information according to the polarization. And there are two bases, common bases that are used to encode information. They are represented in the table on the right. Okay? So we have two binary values, 0 and 1. And there are two bases that are represented here. The first one is the rectilinear basis. Okay? 0 is encoded as an horizontally polarized photon. 1 is encoded as a vertically polarized photon. Okay? And they are orthogonal. You see, they are orthogonal. And we have also the diagonal basis. Okay? So a 0 is encoded as a diagonal photon. And a 1 is then encoded as an anti-diagonal photon, 45 degrees, and 45 degrees. Okay, and these the rectangle within each basis, the encoding is orthogonal, but the bases here are not usually orthogonal. Now I'm going to be very abstract. And I'm going to use to explain how things work in a simple manner. I'm going to use the graphical representation that I have here on the bottom right. Okay? So each circle represents an individual photon. And we have the two bases and 4 encodings that I just described. So we have first cycle is an horizontally polarized photon. It's a 0. Vertical polarization, it's a 1. Diagonal, it's a 0. Anti-diagonal, it's a 1. Okay? And to measure photons, we use filters. I have the squares represent 6 possible filters. I have a filter for horizontal photons, diagonal, vertical, diagonal, and anti-diagonal. And I have filters, 2 filters in the bottom right, for the 2 bases. For the individual polarization, is the block of 4 filters on the left, and for the bases is of course the 2 squares on the right. And the one with this, the cross is for the rectilinear bases, and the one with the 2 diagonals is for the diagonal bases. Okay? So we'll go with that. I'm going to explain now how filtering works. Okay? This is very particular. I have a simple example here. In the middle, we have the vertical filter, and there is a flow of photons going through the filter, left, right. Okay? It's simple. I have 4 examples, 4 photons, the 4 possible polarization. And the example shows how a filter behaves. That's very important for understanding how things work. Okay, the first photon, just left to the filter, is a diagonally polarized photon, anti-diagonal. It encodes a 1. Okay, so what's happening with that photon? It's blocked. It doesn't go through. Okay, the next is another diagonally polarized photon. Okay, diagonal polarity, it's a 0. This time it goes through. Okay? But the polarity is changed to vertical. Okay, so that's something interesting that we're going to exploit. So if you use in that case, we use a vertical filter. And if you submit a diagonally polarized photon to the vertical filter, half of the time it goes through, half of the time it's blocked. When it goes through, the polarities change to vertical. Now the last 2 photons, one of them is horizontal. Horizontal and vertical are orthogonal. So the horizontal photon is always blocked, doesn't go through. And the vertical, of course, goes through unchanged. Okay, so I'm going to explain how the software-defined Stream-Cipher works, exploiting that property, the properties I just defined. Now first, why doing that with the software-defined radio approach? I don't think I will have much difficulties to convince you. Okay? Software-defined communications is to hardware communications. What word processors are to mechanical typewriters. We have more flexibilities, more capabilities, more advanced features. And this exact idea of combining quantum communications and software-defined radio was actually introduced for the first time in the new radio, during the new radio 2011 conference by Professor Barbeau, who is still working on that, and he's working on super dense coding using communication. So why my design would be interested, why you might be interested to look at my design and my code? I think there are 4 reasons. I combine quantum communication with the software-defined radio approach. It's combined, if you have some background in quantum computing or quantum communication, my work is based on quantum key distribution, Q QKD. I use the principles of QKD to develop a stream cipher.
Yeah, I saw that, but I had to run out the door.
Also, I use my implementation is simulation. So new radio was not originally designed for simulation, but it can work well for simulations. That's a simulation example. And it was mentioned yesterday that in new radio you cannot have a cycle in a flow graph. Okay. So I understand very well why. And I use the message passing interface that was described by Tom during his tutorial yesterday, in the last part of the tutorial yesterday. So it's a good example. It's not very complex to understand, but if you face that problem, eventually you can look at how I resolve the problem of the related with the possibility of having cycles in flow graphs. Okay, if you don't have background in cryptography, the Stream-Cipher is maybe the simplest algorithm, one of the simplest to understand. And the Wi-Fi use Stream-Cipher principles. It has evolved over time, but mainly related with the way Wi-Fi establishes keys. So in short, we have three things. Okay? We generate a random secret bit string. So that bit string is secret to the source and destination. We have an encoder and a decoder, and they share this secret string. So I'm going to show how this secret string can be used, can be established with quantum communications. And the bit string, this secret bit string is single use. You use it once, and each time, for each new message, you have to generate a new one. If you don't do that, it won't work well. It makes the protocol easy to break. So the ciphertext, it's easy. This cipher is popular because it can be implemented efficiently in hardware. Okay? So you just XOR, you go bit by bit, you have your plain text provided by the user, you have this random bit string, and you export the two together bit by bit, and you send bit by bit. And the receiver, the decoder, just takes the ciphertext and it XOR the ciphertext with the secret bit string. It's very easy to implement on both sides. Now this is my design, my software-defined radio, my software-defined quantum cipher. Okay, so we have an encoder on the left. We have a decoder on the right. The decoder accepts plain text. The decoder returns the original plain text, ideally. Okay? And I use 4 channels between the encoder and the decoder. Okay, the top 2 channels, they are synchronous, okay, in the sense of new radio. Okay? So one of them is used to model the insecure photon channel. Okay, we send photons, photon by photon, and we assume that this channel is not secure. It can be intercepted by an adversary. Okay, and I will send also with another synchronous channel, the bases that are used to encode the photons. Okay, because to properly measure the photon, you need eventually to know the bases that were used to encode it. On the other side, I use 2 one-way asynchronous channels, and they are based on new radio message passing. So one of them from the decoder to the encoder is used to send feedback, and the other one is used to send the ciphertext. Okay? So only one channel is quantum, the first one. The other three channels are classical channels, or classical bits. And I use the principle of the BB84 protocols. So that is my the BB84 protocol. My work is founded on the BB84 protocol. Okay, now I'm going to run a short simulation of the encoder. So I'm going to explain how the encoder works a little bit. Okay, so once you understand the encoder, you will understand the decoder because they are symmetric. So here I'm going to show how the two synchronous channels work. Okay? So we have time going horizontally, and we have the two channels, the two synchronous channels represented vertically. Okay? So we have the photon channel, and we have the other synchronous channel to which I'm going to send the basis. Now the photon channel is used to establish the secret bit string between the encoder and the decoder. Okay? And of course this channel can be intercepted, so we have to think in terms of that. So the encoder generates randomly bits, bit by bit. Okay? So I'm going to do a simple example. I'm just sending 4 zeros. Okay? So the first one is a 0 encoded with the horizontal polarity. Now the thing is, for the decoder to decode that properly, it needs to know which polarity was used by the encoder. But we don't tell that. Okay? So the encoder doesn't know beforehand, and same for an adversary. So the decoder just picks at random one of the basis filters, rectilinear or diagonal. Sometimes it will be right, sometimes it will be wrong. So with probability 50% in each case. So what it is, when the encoder made the right choice, the bit is usable for encryption. Okay? And the decoder and the encoder and the decoder, they will agree on the bits that can be used for encryption. So what do we do? So right after the transmission of the photon, we actually send the basis that was used to encode the photon. Okay? So we have the blue photon top left, and the instant after, we send the basis rectilinear in that case. And in parallel, we can send another photon. So at time t0, we send the first photon. At time t1, we send the basis. And the decoder is able to confirm if the right basis was used for decoding. So we have, in parallel to sending the basis, we send another photon, the red photon. It's a 0 again. And at time t2, we send the basis. Okay? So the decoder can tell, hey, I actually picked I actually did the right or wrong measurement. And we go like that, photon by photon. There's a yellow photon after that, and I send a green photon. So the first two are in the rectilinear polarity, and the last two are in the diagonal polarity. Okay? So with this, half of the photons will be usable, and half of the photon won't be usable. So the decoder receives the basis, and on the feedback channel, it returns to the encoder the positions of the photons that were interpreted correctly. Okay? And for these photons, the bits that are encoded in the photons can be used by the Stream-Cipher. Okay, so half of the time they are correct. Okay, I don't have much more time, but the code is not very hard to understand. And here I give an overview of the main method that does the work. And there are basically 4 buffers. There is a buffer for the feedback. Let's see, so this is the encoder, the buffer for the feedback. Let's see from the decoder. The encoder also memorized the bits that were sent, and the plain text provided by the user. And this is a case where the feedback is positive. So the bit that was encoded in the photon and a plain text bit is actually sent as a ciphertext. And this picture a case where the feedback is negative. So you can look at the code, it's easy to understand. I believe. Now to conclude my talk, I have I think my slides will be on the website of the conference they are. The code will be there also. And I would like to mention, I teach software-defined radio and cognitive radio. And I liked the presentation yesterday of my colleague, Professor Mattis. I think it was the last talk, I don't know if he's here right now. He's teaching software-defined radio with New Radio. I do the same with MATLAB and New Radio, but I teach it with the computer science perspective. For instance, when FM modulation is explained, I explain FM modulation, but I don't show how to implement efficiently FM modulation. I show how to use the FM modulator in the New Radio library. And I have an open textbook on my webpage. It's open access. You're welcome to consult it. If you have feedback, please communicate with me. And I think it's a good reading, especially if you are using New Radio Companion and you want to understand the little numbers inside the blocks. This book will give you the background you need. And I have a new chapter on FPGA programming, and I explain the implementation of the coordinate algorithm, both in MATLAB and in Verilog. I think it's quite readable. It will give you a good background on FPGA programming. Thank you very much, and I can handle questions if you have any.
All right, distinguished students. So we have time for a question or two while we get set up. Oren, I'm going to ask you to come up and start to use the mic. Are there questions from the audience? Yes, here we
Professor Barbeau. I'm Pascal from Michel University. I was wondering if you were using any kind of error correcting codes in your system, and if yes, what kind?
What kind of code?
Error correcting codes.
Not right now. Not right now. That could be a possible extension to my work. You're giving me an idea for an exercise for my students, actually. Thank you very much.
Well, maybe we can talk offline. It's just
Sure.
I work on the error correcting codes, and we've had people working in the field of quantum key distribution come to us asking questions. Apparently, this afternoon is interesting for your application.
Okay.
Thank you.
So I had a question about the feedback. So I didn't quite understand what the feedback was doing and how it worked.
Yeah, because the feedback is very important. Because half of the time the decoder doesn't know in advance which basis is used. by the encoder to encode each photon. So it picks one at random. Sometimes the decoder picks the right basis, so the photon is decoded properly. And after of the time, the decoder picks the wrong basis, the wrong filter. So the photon is not decoded properly. The outcome is random, 0 or 1. So it's usable just when, the bit is usable just when the right filter was. So the decoder tells, okay, for that photon, I use that filter. The other one, I use that filter. And the encoder confirms. So, okay, this time it did right, this time it did wrong. So it determines the bits that can be used for ciphertext. And the bit string actually remains secret for the encoder and decoder that way. Very important.
All right, that's all we have time for. Let's thank our speaker one more time. Thank you, Michel.